Can you hear me? Oh, okay, I hear myself. That's a good sign. That means that we can hear us soon. So, okay, now let me ask a question. If you're able to hear me, please send a message into the chat relay saying, "Hi, I hear you." Okay, all right. So this is good. Sorry for the delay, guys. So you can hear, is that right? Did anyone say you can hear us? I hope that's a yes. Okay, right. You can hear. Okay, very nice. And we can start now. Sorry for the delay. The reason for the delay is because this, if you can't tell, this is a mega meeting. So we have lots and lots of people in here, and there were some delays in getting started because when there are this many people in a meeting all excited about math, well, then things kind of blow up. Well, in any case, welcome. I'm Po-Shen Loh. I am the host in some sense of this meeting, but I am joined by two incredible people and I'll introduce them in a second. But I want to let you know what we're going to do today. We're going to be doing an AMC 8 live solve. In fact, I wanted to solve the problems too, but I'm actually having technical problems with my sound, so I can only join you from here. I wanted to join you from there. So what we're going to do is we're going to be going over the questions on the 2025 AMC 8. Actually, I haven't even looked at them before, other than typing them up. And that was on purpose. I want to actually have some fun thinking about how to solve these questions to show you how we go about solving a problem if we've never seen it before. With that, the style that we're doing this in is that I'm only one of the three. In fact, I'll be taking turns together with them as we go through and do these problems. But I'm only one of the three because we have two other incredible people. And I'll actually introduce both of them. First of all, let's see. We usually go by first letter of first name. So I guess that Anshul will be the first. Anshul, can you just say hi because then you'll take over the screen?
Oh, hello everyone. Hope you all can hear me. But hello.
Yeah. Well, I can hear you. That means that they can hear you because our room's going to theirs. So that's Anshul. He's very interesting. He's been helping to teach over here in live for a while. He's a four-time Amy qualifier. He was also a qualifier for the USA Physics Olympiad in 2023, and he enjoys basketball and chess in his free time. We also have Vivian Tan. Vivian, do you want to say a sound so you pop up?
Hello, everyone. Can you
Great.
guys hear
This
me?
Had to be because I saw you took over that screen. So you're through. Vivian's awesome. She's also done math contests for a while. She's an Amy qualifier since 8th grade. She's the math club president and a math counts coach, passionate teacher. Actually, you're also a dance champion. Is that right?
Yeah, I do Chinese classical dance.
Yeah, that's right. We have lots of fun people here today. So with that, if you can't tell, this is a rather dynamic meeting. So whenever you have any ideas, please send them to chat relay. That's how our system works here. You choose in your Zoom chat to send a message to chat relay and pow, it will have a chance of appearing on the screen. I say a chance because if everyone gets super excited, then not every message gets on the screen. And if you say things that aren't so nice, I have to apologize. We have moderators who will knock that out. And the more things that you say that aren't nice, the less likely you'll be able to talk. So say good stuff. And then if you say good stuff, who knows? You might even get a star. That's what happens when you say like a good math idea. But with that, let's dive in and start doing some problems. We're going to start doing alternating between the two of them. I'll be trying to connect my sound in so that I can join in. But even if I am not in yet, I'll make comments here and there. Sound good? Anshul and Vivian, do you want to go by first letter, first name again?
Yeah.
Uh,
So, Anshul, you can go ahead.
all right, cool. It's nice to meet you all. And here we got the first problem, right? We're given like pretty much 8-pointed star, right, in this sort of like quilting pattern, and we want to figure out what percent of this entire grid is covered by the star, right? So as you can see from the diagram, we're pretty much split into a lot of these triangle shapes, right? What we can do here is we pretty much can just count these triangles, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? As you can see, we have 16 of these small triangles, and we have 16 of these total squares, and we know that one of these triangles is half of a square, right? So I see a lot of people, yeah, I'm getting option B, right? Because we have exactly the number of triangles as the number of squares, and the triangles have half the area of the square. A lot of people got it, so really nice job, everyone. Thank you for all the help.
Yes, awesome. Okay, so that was a pretty quick and easy first question. So now let's take on question number two. Now, question number two has a lot of information on it, so let's just take a moment to look at it in case we've forgotten from taking the AMC a few days ago. So we just have a ton of hieroglyphics which were used by the ancient Egyptians, and then it tells us how much each hieroglyphic is worth. And then it's asking us to find what number would be represented by these hieroglyphics right here. Now, since we have a key over on this side, we can just use that key to help us find the number it represents. So we would have to add up the hieroglyphics together. So this long and skinny shape over here, it kind of looks like a finger. It tells us that is worth 10,000. So we're going to have one of those. We have 1 times 10,000. And then we have 1, 2, 3, 4 of these like kind of swirly things, right? So you want to add 4 of those. And how much are each of those worth? Those are each worth 100. So we're going to add 4 times 100. And then we're going to move on to the next shape or hieroglyphic. It's kind of like this upside down U kind of shape, right? And we have 2 of those. So we need to add 2 times whatever the key says is worth 10. And then lastly, we have 3 vertical lines, which are each worth 1. So that's just 3. And if we add those up all together, we would end up getting an answer of 10,423, making answer choice B our final answer for question number 2.
All right, guys, we're on a roll. We already got 2 done, and now we're on to this game, right? Buffalo Shuffle, interesting name. It's a card game where we have these cards that are evenly distributed among all the players that at the start of the game. And we have Annika and her 3 friends, right? So we have 4 people, right? And if we have 4 people, now we're gonna have 15 cards, right? Always good to write down our values. So 2 more friends join, right? And with 2 more friends join, that means we're gonna have 4 plus 2, 6 people, right? So if we look at the initial value, we have 4 people and 15 cards per person. So we're going to have 60 cards in this case, right? Simply just 4 times 15, right? And then now we just divide. Now that we have 6 people, we split them up and we do 60 divided by 6 in order to get 10, right? And pretty straightforward. And I see a lot of you also agree. So let's see if we're right. And lo and behold, we are correct.
All right, awesome. Nice solution for question number 3. Okay, so now if we move on to question number 4, we have Lucius, who is counting backwards by 7, and his first 3 numbers are 100, 93, and then 86. Now, the question is asking us, what is his 10th number? Well, there are multiple ways that we could approach this problem. Honestly, we can just list out every number one by one and find the 10th one, but an easier way to do this is just to start with our first number, which would be 100, and then minus a certain number of 7s. Now, if we think about this, when we minus 1 7 or subtract 1 7 from 100, it gives us the second number. And when we subtract 2 7s, it gives us the third number, 86. So in order to find the 10th number, we would have to subtract 9 7s. So we're going to do 100 minus 9 times 7. 9 times 7 is just 63, so this entire equation would just equal 37, making its choice B, like what you guys put in the chat, as our correct answer for question number 4.
All right. Already 4 down. And we're on to the next problem. Now we're given a grid, and we say Betty drives a truck to deliver packages, and we're given a street map, and we start at factory. We'll call that F right here. We're gonna go drive to location A, then B, then C, and then back to F, right? And pretty much all we have to do is, and each one of these side lengths is 1 by 1. That's always good to know. All of our side lengths are the same. So all we have to do is sort of just count up along this path, right? Just go down, across, here, right? And then an even shorter way to do this is we can just imagine this as a cube almost, right? Because if we sort of extend this outward, we're just gonna get a rectangle. I'm sorry, not a cube. It's obviously 2 dimensionals. But now all we have to do is count the edges of this. We're gonna get 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 7 by 5 rectangle. All we have to do now is solve for the perimeter. 7 plus 5 times 2, that's going to be 12 times 2 to get 24. So should be right, and I see a lot of you got it as well, and that's what the answer is. So nice job, everyone.
Okay, nice. All right, on to question number 6. So now we have Seiko, who writes the numbers out 15, 16, 17, 18, and 19. And after he erases one of those numbers, the sum of the remaining 4 numbers is a multiple of 4. We're trying to figure out which number he erased. So in order to approach this problem, one way that we could think about it is, first let's take the sum of all 5 of the numbers. So if we were to add up 15, 16, 17, 18, and 19, the sum would just equal 85. And then what happens is we take away one of those numbers and that becomes a multiple of 4. Now, what I notice about 85 is it's just one more than what a multiple of 4 could be. So like, for example, 84 is a multiple of 4, but 85 is just one more than that. So if we're trying to take away one number to get to a multiple of 4, the number we want to take away also has to be just one more than a multiple of 4. And what I mean by that is like, oh, if we divided it by 4, it would have a remainder of 1. So if we look at our numbers that we could choose from, 15, 16, 17, 18, or 19, 17 is just exactly one more than a multiple of 4. So that would make 17 the correct number to remove in order to make the sum of the remaining 4 numbers a multiple of 4 as well. And it seems like you guys also agree with answer choice C.
Oh. All right, guys, we're on to problem 7 now, and we're given Professor Sochi class. No clue how to say that name, I'm not gonna lie. But, so 5% of his students get a 95%, 13% students, 5 students get at least a 95%, 13 students get at least a 90%, 27 get at least 85%, and then finally 50 get at least 80%, right? And now we're gonna find the number of people that get at least 80, but less than 90, right? And we can just really think about this as there's 13 students above 90, and there's 50 students above 80, right? So we can sort of just list. So all we have to do is take that total amount of people above that 80 threshold and then subtract out the ones above 90. So all we have to do is do the 50 minus the 13, the total number of people minus the people above that score, and 37. I'll see a lot of people had that same step as me. So really nice job. And then we're gonna hopefully, and then there it is. So really nice job. A lot of people had that exact same steps as me.
All right, moving on to question number 8. Now we have Isaiah who cuts open a cardboard cube along some of its edges to form this flat shape shown on screen. Now it tells us that the area of this shape is 18 square centimeters, and we're trying to figure out what was the volume of the cube in cubic centimeters. Now, since we have this shape here, when it gets folded up, it forms our cube, right? Which makes each of these little squares within this shape one of the faces of the cube. And in order to find the volume of the cube, that would be like taking the side length of one edge and cubing that, right? So we want to figure out what one of these side lengths would be. In order to do that, what we can do is we can take this total area of 18 square centimeters and divide it by 6. And why 6? Well, there are 6 faces, and since they're all the same size, they would have the same area, and we can determine that the area of one of these square faces is just going to be 3. Now, what do we do with this 3? This 3 represents the area, right? So that would be the same as taking one of these side lengths and multiplying it by itself, making, let's say the side length is x, x would equal the square root of 3. So if x is the square root of 3, we're trying to figure out what x cubed would be. So if we know x squared is 3, and we know x is square root of 3, then x cubed would just equal 3 root 3. So that would make our answer 3 root 3, or answer choice A. So let's check our work. And yes, looks like we were correct. Nice job, everyone.
All right, we're on to problem 9 now. We're already, more than almost like a third of the way in. But so now we're on to this question. We're given a clock, right? And we basically take these sort of pairs on opposite ends where we have 12 and 6, 1 and 7, 2 and 8, and we have all of these. We take the average of those two numbers, and then we average all of those numbers together, right? And instead of really actually just calculating all of these by hand, you can just add them all together, right? Each one of these is considered exactly once, right? There's no time where we'll have another opposite pair, right? There's only one number that's opposite to another number, right? So all we have to do is look for the average of 1, 2, 3, all the way to 12, and we don't even have to calculate that as well. We can just do 12 plus 1, right? We can add the two extremes values and just divide by 2, and just get 6.5. So you can really circumvent a lot of the sort of calculation that might be involved, which could definitely help on your own AMC test. But a lot of solutions definitely work for this. Oh, and there it is, 6.5. So really nice question.
Yes, very nice. All right, we've reached question 10, you guys. Let's do question 10. We have these two rectangles that are, the same size, but one of them is rotated among this midpoint of CD in order to overlap them. And we're trying to figure out what the total area in square inches is covered by the two overlapping rectangles. And well, this shape honestly is kind of weird, but one way we could figure out this area is by adding and subtracting the area of the shapes that we see. So first off, we have rectangle A, B, C, and D, and then we have another rectangle of the same size. So what we could do is we could add the area of ABCD plus its own area another time. And then what we could do is we could subtract the area of this shape right here, because this little square in the middle is the overlap of the two shapes. And we want the total area, so in order to get that, we have to subtract this overlap, because we're technically counting for it twice if we just add the area of the two rectangles. So in order to do that, we would first take the area of one of the rectangles, which if we have AB equals 5 and AD equals 3, that would make the area 15, and we want to have that twice. So we're going to do 15 plus 15, and then we want to subtract this square's area. And how can we find the square's area? Well, it tells us that ABCD is rotated around the midpoint of CD. And it also tells us that CD or AB is equal to 5 inches. So that would make the midpoint right here, if that's the midpoint, that would make it this section of the square equal to 2.5. And again, using the formula for the area of a square, we can just square that in order to find the area. So that would be minus 2.5 squared. And so our final answer, if we do 30 minus 2.5 squared, would be 23.75, giving us answer D. Let's check our work together. And yes, it is indeed answer choice D.
Wow, that's good. Actually, I'm curious. Does my sound work now?
Yes.
Yes.
Wow. Okay. Then in that case, I can come and join the whole party. I'm so sorry. I wish I could have joined earlier because this was fun. First of all, I hope you guys had some fun because I certainly did. It's always great to watch amazing people solve problems. And at this point, you see that actually, you probably don't need to watch me solve problems. Anshul and Vivian are awesome. But anyway, we'll take turns, and I want to try too. So what's this? This looks like Tetris. What's this about? So it says a tetramino consists of 4 squares, and that's actually why it's called a tetra. Tetra means 4. And so it's got 4 squares connected along their edges, which is like this. And there's like 5 possible tetramino shapes. I guess they're called like I, O, L. I guess that looks like a T, and this is an S. Okay. And you can move them around, and you can even flip them over, it says. That's important. And it says we're going to cover a 3x4 rectangle using 3 of these, which makes sense because each one has 4. And it says one of the tiles is an S tile. So what are the other 2? So somehow I need to go and cover a 3x4 rectangle. Let's see. Can I draw? Let's try to draw. So the hardest part about this question is trying to understand it. So if I have one of these tetraminos, okay, so it's a 3x4. Can you see? Yes, you can see. Let's do this. So if I have a 3x4, the hardest part of this question is trying to understand what we're supposed to do. Where can we put the S? I guess that's how I think about this. So for the S, what if we put it here? Oh, it actually works. Oh, that's cool. So the hardest part about this question is understanding it. It looks like if I put the S here, because that seems like the only reasonable place to put it, it looks like the rest of it is 2 L's, right? Because if you're going to put the S, don't make it so that it blocks down the middle, you get stuck. So if that's the case, is there a choice for 2 L's? Because it says there's only one answer. So I'm going to go with C. Wonder if that's right. Yay! I guess I'm okay at playing Tetris. With that, I'll turn it back into the sequence of what we're doing, and I'll now jump in every third one.
All right, all right. We're on to problem 12 now. A really interesting problem once again. And this time, we're given this sort of diagram with 12 squares, each with 1 centimeter side length. And we want to know what's like the sort of largest circle that we can put into this diagram, right? So it might seem kind of like hard to do this, right? Because it's such an unnatural shape, right? When you think about it, like how do we know where the circle will line up? So if we just think about it, So a larger circle would obviously have to be centered in the middle because we have a perfectly sort of symmetric diagram. So, a circle here, like that size, obviously we can extend it, right? But how far can we extend it? We can only extend it to the closest point to the center, right? Which would be right here, or right here, right here, or anywhere around one of those points, right? Past that, then we can't go past the circle or else we're no longer within the boundaries, right? So all we have to do now is look from the center to the closest possible point, right? This is going to be our radius. So this length, right? Oh, I misdrew that. This length would be 1, and we have a side length 2 here. Now all we have to use Pythagoras theorem, right? We use 1 squared plus 2 squared, and we take the square root, right? That's going to be square root of 5, right? So if we have now our radius is square root of 5, right? Radius is square root of 5. Let me try to draw this circle. Alright, that's the best I can do. Square root of 5 squared, right? We know the area of a circle is pi r squared. So all we have to do now is take the square root of 5, we square it, so it cancels out, and now we have 5 pi. This should be the answer. Maybe let's check our work now. Definitely a hard problem, and lo and behold, the answer is 5. So really nice.
All right, yes, very nice. Okay, on to question 13. Okay, wow, it looks like we've got some graphs here. Okay, let's read the question. Each of the even numbers 2, 4, 6, ... to 50 is divided by 7. The remainders are recorded, and we're trying to figure out which of these histogram graphs accurately displays the number of times each remainder occurs. Okay, this is a really weird question, you guys, and honestly, I can't really think of a really clever way to start it, so I kind of just want to, try some numbers out. So, since it tells us we have even numbers from 2 to 50, let's just write some out. So we have 2, 4, 6, and we're going to take those and divide them by 7 and get the remainders. So I'm going to use a little line just to represent like some separation, but underneath I'm just going to write what the remainder would be if I divide it by 7. Well, since these are all under 7, the remainders are pretty easy. We get 2, 4, and 6 again. But what if we keep going? What if we use 8? Well, then our remainder becomes 1. What if we use 10? Our remainder becomes 3. Okay, these are all different numbers. This isn't really helpful. Let's keep going a little bit. Let's try 12. Well, 12, if we divide it by 7, our remainder becomes 5. And then if we keep going and we go to 14 and we divided that by 7, our remainder is 0, right? Because 14 can be evenly divided by 0. Well, what if we keep going and we go to 16? 16 divided by 7, the remainder, well, we can take 14 out. The remainder would just be 2 again. And if you keep doing that, you'll notice that this pattern actually repeats, where your remainders will go from 2 to 4 to 6 to 1 to 3 to 5 to 0. And that's going to occur every 14 numbers. Well, if we use that information, then we can just take our biggest number, 50, since we go up until 50 and the pattern repeats every 14, well, we can just first divide by 14, and that's how many full occurrences of this pattern that would happen. So 50 divided by 14, well, that's gonna be, let's see, hold on, that's like 3, right? Yeah. Okay, that would leave us with 42, and then we have some numbers left over. So if we were to do 14 times 3, that would give us 42, and so our next even number would be 44. So we can get rid of the rest of this work up here and start from 44. So we have 44, 46, 48, and then 50. And now we just need to find those remainders. 44 divided by 7. Well, we can take out 42, and so our remainder would be 2. And then for 46, we would get 4. And then for 48, we would get a remainder of 6. And for 50, we would get a remainder of 1. So these are like the extra occurrences of each of these remainders. So now we need to look back at our answer choices and figure out which answer choice shows a graph that has all of the remainders even, except these ones occur one more time. And looking at the answer choices, I think A fits this perfectly. We have 0, 1, we have all of the numbers at the same level except for 1, 2, 4, and 6 having one more than each of the rest, making our answer A. So let's check, make sure we did this correctly, and yeah, it looks like we did. Nice job, everyone.
Yay! Okay, so this is great. And I also have to apologize. My system is not as cool as theirs, as you can see. I don't have any lights. And unfortunately, the chat really is not working for me. But the thing is, I can see all the messages you're sending because we have an internal system. So let's just keep on going. And in between all of these, I'll try to see if I can keep making mine work. What's this? This says the number n is inserted into this list, 2, 6, 7, 7, and 28. The mean is now twice as great as the median. What is n? Huh, that's an interesting question. So, okay, when I look at this, this is different because they're different than how I would do a question normally because there are answer choices here. And if there are answer choices, I can already see what kind of things the median might be. That's actually how I'm going to think about this. For example, if I add a number, let's start with the middle. If I added 20, what would the median be? You can type into chat relay and think, what would the median be if I put 20 in there? If 20 is in there, I would have 2, 6, 7, 7, 20, and 28. And so, okay, I see people are answering. So the median is actually going to be 7 in that case. That's interesting. So if I throw in 20, the median is going to be 7. Oh, this is interesting. Look, no matter what number I throw in, what's the median? Because what if I didn't throw in 20? What if I threw in 7? Oh, the median is still 7. Is it that easy? In the sense that at first I wasn't sure if the median would change. Like if I threw in 34, what's the median? It's still 7. So then this is telling me that when I think about the word median, I should just be thinking median is 7. Okay, everyone type in the chat really because I can see what you're typing. So what is twice the median? So it says that the mean is now twice as great as the median. So that tells me that the mean should be, thank you, I see it. You guys are answering in chat, so I see it. So you're telling me that the mean has to be 14. Well, if I know what the mean is going to be, if I know what the mean is supposed to be, and how many numbers do I have? I'm going to have 7 numbers. No. How many? Yeah. Wait a second. Did I do that right? Wait a second. Oh, no. No. This is not right. This is not right. I take it back. I made a mistake. The reason I made a mistake is because the median is not always 7. Okay, so by the way, what you're seeing here is that when someone solves a problem, they don't always know exactly what they're doing right away. So in particular, in those cases, wait a second. No, I am convinced. The median is always 7. Yeah. I was slightly worried because, you see, I paused for a moment because I was wondering, is there an even number or an odd number of things? But no matter what number you add, there's going to be 2 7s in the middle. So the median is always 7. So it's okay. But in the end, what I have is I have 6 numbers, mean of 14. So what's the sum? If I have 6 numbers, the sum of all 6 numbers is going to be 6 times 6 times, mean is 14. So the sum is going to be 6 times 14, right? So I need to know what is 6 times 14. I see people typing it into the chat. You're right. This is equal to, what is it? So 6 times 4 is 24. 6 times 1 is 6 plus 2 is 84. So I need to have a sum of 84. In that case, now let's look at my original numbers. So I know I need a sum of 84, and let's see the original numbers. Oops, I didn't want that. You didn't see that. I didn't see that either. So I thought that the numbers might appear on the next screen. But we have all these things here. I have 2, 6, 7, 7, and 28. I need to make a sum of 84. What is 2 plus 6 plus 7 plus 7 plus 28? Well, what's the easiest way to do this? I'm just going to go left to right. So 2 plus 6 is 8. This is an 8. 8 plus 7 is 15. 15 plus 7 is 22. Okay, I just double checked that in my head, by the way, by doing 7 plus 7 first. Got 14 plus 8, that was 22. So I know this part is 22. 22 plus 28 is equal to 50. So you see, I like to check my work as I go because it's very easy to make a silly mistake. But now, if I've got 50 here and the grand total is supposed to be 84, what's left? That means that what's missing is E, is 34. So, and that is indeed the answer. I'll turn it back to my teammates while I try to fix my chat.
All right. So we're on to problem number 15, and we're given this 6 by 6 grid, right? So we're going to get 36 squares pretty much. And 13 of these squares are going to be colored silver, and the remaining squares will be colored gold, right? So let's just write that down. And then 13 and 36, right? And then he's going to fold it on like this pretty much. He folds it over like vertically, and he forms like these like basically where they like sort of overlap, right? Once we fold them, of course. So like lowercase m is going to be the least possible number of gold on gold pairs, and then uppercase m is going to be the highest possible number of m's, right? So if we have 36 squares, how many pairs are we going to get, right? We're simply just going to get 36 divided by 2, right? Because each pair is 2 things, and we just divide by 2. So we're going to get 18 pairs, right? If we want to minimize this, we're just going to try to have as many of these silver gold pairings as possible. So we take away all of the gold from pairing with other gold, right? So we have 13 gold silver pairs, and we have 18 total pairs. How many gold pairs we have in the smallest case, right? And in that case, we're just going to have 18 minus 13, right? We subtract out all of those, like the ones with the silver, and we're going to be left with 5. I'm just going to go to the next page. I'm running out of the little room here. So we're going to get, in the smallest case, we have 36, so 18 pairs, and 13 silver, and the rest are gold. And in our smallest case, we have 8 minus 13, or just 5. And now we think about the opposite, right? How do we maximize these number of gold pairs? In order to maximize the number of gold pairs, right, we also want to pair up the silver with just the silver, so we keep the gold by itself. So in order to sort of keep these, we're going to have 6 of these pairs, and we're going to have this one leftover silver guy, right? He's not going to have a partner. So in that case, we're pretty much going to have just 7, right? 7 of these things that we cannot pair up. So 18 minus these 7 that we can't use, that's just going to be 11. And now all we have to do is add our lowest and our highest, right? 5 plus 11, 5 plus 11, that's going to be 16. And now we just check our work, see if our logic is correct, and it's correct. So really nice job. Hope you all followed along. Really interesting problem.
Yes, awesome job on that question. Okay, on to question number 16. So we have 5 distinct integers from 1 to 10. Well, we choose 5 distinct integers from 1 through 10, and then we choose another 5 distinct integers from 11 to 20. And out of those 10 numbers, no 2 numbers differ by exactly 10. And then we're trying to find the sum of the 10 chosen numbers. Okay, let's think about this for a second. If it tells us that no 2 numbers differ by exactly 10, that means one of the numbers and another one of the numbers in this set of 10 numbers, they can't have the same units digit, right? Because let's say we had 1 and we had 11. They both end in a 1, and so their difference is exactly 10, and we don't want that. So, because no 2 numbers will differ by exactly 10, that tells us that all 10 numbers have a distinct units digit. They all have a different units digit. So first of all, we could just first write out 1 plus 2 plus 3 plus 4 all the way until 10, because that would take care of each of our units digits, if that makes sense. I know 10 isn't exactly a units number, but 0 isn't a choice, so you'll see why it works out later. So this accounts for all of our units digits, and then we have to account for the other numbers. And, well, 5 of these numbers are going to be 10 bigger, because we have 5 from 1 through 10, and then 5 from 11 through 20. And right now, we're just going to pick some random ones to make, instead of 2, we would make them to 12, or instead of 4, we would make it to 14. And, well, it doesn't really matter which ones we increase by 10, we're just adding 5 tens, if that makes sense. So we would just add 50 onto the end. So if we add 1 through 10, that would just give us 55. And then we add on 50, so that would just give us 105. So I hope this whole units digit makes sense. Since, no of the 2 numbers will differ by exactly 10, it just means that all of the numbers are going to have a unique units digit, which makes our answer C. Let's check and make sure we did it correctly. And yes, looks like we did. Good job, everyone.
Hello. Okay. Good job. Let's see. What's next? Oh my gosh. Why are there so many words? Okay. Looks like we got a AMC test in reading. In the land of Markovia, there are 3 cities, A, B, and C. And again, I can see everything you guys are typing. So if you type stuff, I'll see it. Don't worry. So, right, there are 100 people who live in A, 120 people who live in B, and 160 who live in C. Everyone works in one of the 3 cities. Okay, I guess I'm covering the cities. Cities look like that. Everyone works in one of the 3 cities, and a person may work in the same city where they live. Okay, that makes sense. Hopefully you do. Otherwise, you got a lot of driving. In the figure below, an arrow pointing from one city to another is labeled with a fraction. Oh, I see. It's the fraction of people living in the first city who work in the second city. For example, 1/4 of the people who live in city A work in B, because there's a 1/4. That's right. How many of the people work in A? Oh, okay. So then how could you possibly end up working in A? The only way to end up working in A is either to live there already or to come in from somewhere else. Okay. I am going to hope that the next screen gives me some space to draw. If it doesn't, I'm going to flip back right away. Good. I have space to draw. I don't want to see the answer. Okay. So, right. Oh, wait. I need to know how many people are in each city. Let's label it. A has 100 people. So there's 100 people here. B has 120 and C has 160. Okay, so that's A, B, and C. Now I need to know how many people work in A. So there's 3 ways to come there. First of all, you could start in A and work in A. So if you start in A and work in A, that's 100 times what fraction? Oops. I want to draw times. 100 times what fraction? So what fraction of people are going to stay inside A? Well, let's look at who goes out of A. There's a 1/4 going this way. There's a 1/5 going that way. Okay. So we're going to lose a 1/4 and a 1/5. Wow, what's the easiest way to do that? I actually don't really want to subtract those fractions. I'm going to do it this way instead. Let's write some words. How many people leave A? Leaving A is 100 times a 1/4 plus a 1/5. Do you know why I want to do it this way? It's because I can divide 100 by 4 and by 5. Okay, so 100 divided by 4 is 25. 100 divided by 5 is 20. So 45 people leave A. That means that how many people stay in A? That means 100 minus 45, that's 55 people stay in A. By the way, if I ever make a calculation mistake, please jump right into the chat because I can see what you're typing. Okay. Well, how about the people who are coming from B or coming from C? From B, how many people go from B to A? B going to A. This is easier because I just have to look at the migration pattern. So I have 120 from B times, how do you get to A? It's this one. Yes, thank you. I see everyone's posting in the chat. So 120 times 1/3 is equal to 40. Okay. And the last one, how many people are going from C to A? C to A, there's 160 in C. Multiplied by, how do you get out? Oh, that's actually not bad to multiply by. Multiply by 1/8 equals my head. Well, anyway, it's 20. Okay, so now I need to add these numbers together. So I have, what is this? 45, 40, and 20. I think that we have to add those 3 and get an answer. 45 plus 40 plus 20. So I'm getting, I think that's 105. Is that a choice? No, that's not a choice. That means I made a mistake. Help, guys. What happened? So let's see. Oh, no. I just can't. I can't read. Yeah. By the way, thank you, AMC makers, for not making an answer choice, which was that one. So I added the wrong numbers. I don't want 45. I want 55. 55. Now this thing becomes nicer because 45 upgraded to 55. Now I have 115. So I'm going to go with this number here. Is this right? Thanks, AMC. Okay, I'll pass it back on to, I think Anshul's next.
All right. On to problem number 18. A really interesting diagram this time. We're given these 2 circles pretty much. And, oh, I slipped. 2 circles, and we want to, and basically the area of these 4 of these sort of shapes right here is going to be equal to this one larger shape, right? And now we want to find the radius. If this length is 1, what would this length r be, or radius, right? So now, actually, I'm just going to move on to the next page, make this a little bit more clean, right? Let's just sort of, how are we supposed to compare the radius of this sort of weird shape, all these 4, to this one, right? That's a little messy, right? So let's just focus on one of these shapes for now, right? One of these shapes is going to be 1/4 of this area, right? And so basically, this area is going to be 4, and this is going to be 1, right? We can pretty much sort of call these ratios, right? And now that we have the ratio of one of this to one of this, right? We can know this important property of area, right? If we have a cube, for example, right? Or like this cube, right? If our side length is 1, we have a 1 by 1, and now we go to a 2 by 2, right? Our area does not just double, right? It becomes 4 times greater, right? That's an important thing to know. It happens to, pretty much in every shape, right? Because if you think about it, we can split this up to extremely, extremely tiny cubes, right? Pretty much. So if we want to try that same idea, in order to quadruple our area, all we have to do is sort of double our side lengths. So we do 2 times our lengths. So everything is scaled to be 2 times bigger. So 2, 2, 2. Now this length is going to be exactly proportional, right? So now we have another 2. So hopefully my logic is all good, and let's look at the answer. Oh, lo and behold, it is correct. So really, really nice solution for this one.
Yes, definitely. Okay, on to question 19, which again has a lot of words. I don't really like all these word problems, so let's, try and digest these words and break the question down a bit. We've got 2 towns, A and B, and they're connected by this road, and this road is 15 miles long. Now, each of these sections of the road have their own speed limit. So, let's say there's like cars, like these 2 cars traveling from town A and town B, and they're meeting somewhere in the center. And we're just going to hope that they follow the speed limit, all right? We're just going to say they follow the speed limit. Exactly. And so if A is traveling this way and B is traveling this way, and they meet at one point, we're trying to figure out how far from town A in miles will the 2 cars meet. Okay, that's a lot of information. I'm going to use a bigger picture, so hopefully you guys can see better. But if we're taking, let's say car A, and we're going from town A, let's first figure out how long it takes us to travel this first 5 miles. And, well, if we have 5 miles and we have a speed of 25 miles per hour and we're trying to figure out how long it takes, what we can do is we can take the distance, or 5 miles, and then divide that by the speed, which is 25 miles per hour. And that would give us a time of 1/5. And this 1/5, keep in mind, is in hours. So for car A to travel this first 5 miles, it takes them 1/5 of an hour. All right, now we got to figure out B, right? How long does it take for car B to travel its first 5 miles? Okay, well, if we do the same thing, we can take 5 miles and then divide by 20 miles per hour. And I'm actually going to do car B in yellow. Divided by 20 miles per hour, which gives us 1/4. So car B takes 1/4 of an hour to travel its first 5 miles. Now, we know that these 2 cars are going to meet somewhere in the center. We just have to figure out where. And since, when they meet, they will have traveled for the same amount of time, so their total time from leaving from their town to meeting somewhere in the middle is going to be exactly the same. So what we could do is, okay, I have an idea, you guys. I'm going to erase those calculations real quick, but if we take our car A, we know it's already traveled 1/5 of an hour. And we know that car B has already traveled 1/4 of an hour. Well, their total times are going to be equal, right? But we need to account for the time that they spend in this middle area. So let's say the distance from town A is 5 miles plus some random distance, we don't know what it is, x, okay? So if A has traveled X amount of miles, we're going to use the speed 40, and we're going to say, oh, they've traveled X over 40 mph. And that's going to be the amount of time they spend traveling from this 5-mile mark to somewhere in between this middle area. And we're going to do the same thing with with car B. And well, they're going to travel this distance, which is the same as 5 miles minus X. So their distance can be written as 5 miles minus X because it's just the opposite of where car A was, since they're meeting somewhere in the middle. And then they're also traveling at 40 miles per hour, so we can divide that by 40, and I need to write my addition sign, but this is like a way that we could write out their amount of time. Since they're traveling for the same amount of time, these two expressions have to be equal. And now we just need to solve for X. Okay, well, how do we do that? Let's first get rid of some of these fractions. What we can do is, let's see, why don't we try multiplying everything by 40? Yeah, that seems like a good idea. Let's try multiplying everything by 40. So 40 times 5, or yeah, 40 divided by 5 is just 8, and then if we times 40, we get rid of the fraction, we just have x, and that's going to be equal to, if we do for car B, 5 minus x times 4, or over 40 times 40, the 40 cancels out. We have 5 minus x, and then 1/4 times 40 would just be 10. So we've converted our expression into 8 plus x equals 5 minus x plus 10. This, if we combine like terms, can be rewritten into, we can move the x to this side, we get 2x equals 5 plus 10 is 15, subtract the 8 is 7, so that means our x is going to be 7 over 2, or 3.5 miles. So this section x is 3.5 miles, meaning that from where town A is, car A will have traveled 5 plus 3.5 miles, giving us 8.5 miles. Okay, hopefully we did that correctly. Let's go take a look. And yeah, it was correct. Answer choice D.
Yay! Okay, you guys are doing really well. I seem to be making all the mistakes. Let's try. Let's see what's next. What's this? More words? Okay. Sarika, Dev, and Rajiv are sharing a block of cheese. They take turns cutting off half of what remains and eating it. First, Sarika eats half of the cheese, then Dev eats half of the remaining half, then Rajiv eats half of what remains, then back to Sarika, and so on. And they stop when the cheese is too small to see. About what fraction of the original block of cheese does Sarika eat in total? Well, let's see. So first of all, when is Sarika? Oh, Sarika gets the first. Okay, Sarika gets the first half. So it's interesting to think about how much. Okay, you know what I'm going to do? I don't know if there's space. Can I ask my teammates, is there a blank slide after this for me or not? Just like let me know and just tell me. Is there a blank slide? No, no blank slide. My teammates are saying no. That means I'm going to have to find a way to draw over there. Okay, I can do that. So if I'm thinking of this, Sarika, the first bunch that Sarika gets a quarter. No, Sarika gets half. That's the first thing because Sarika is half. Then the next person is Dev. How much does Dev get? Well, Dev gets a quarter. Okay. So yes, I see people typing it in the chat. Okay, Dev gets a quarter. And then there's Rajiv. And how much does Rajiv get? Rajiv gets the next amount. Well, the next amount is going to be half of what remains. That's 1/8. In fact, the amount that they get every time just keeps cutting in half. Okay, etc., etc., etc. Well, here's what I'm going to do. The next row is going to say how much they get as they keep sharing the cheese. So Sarika, the next batch she gets is 1/16. Okay, and then actually, if you look at what's happening, how do you get from 1/2 to 1/16? What do you multiply by or divide by? Because that's what's happening. Because what Sarika gets every time is being cut by a little bit. So in fact, that factor is multiplying by 1/8. So that actually, let me write 1/8 a bit more clearly. 1/8. So actually, what's happening is Sarika's going to get, it's called an infinite geometric series. Sarika is going to get 1/2 plus 1/8 sorry, plus 1/16 is 1/8 of that, plus 1/8 of that. Oh, that's too big of a number. I happen to know what that is. That happens to be 1 over 128. But in general, if I'm adding all these together, in general, I can think of it as it's a half plus a lot of powers of 1/8. Okay, so this is a half times. It's a half times. If you factor out the half, it's 1 plus 1/8 plus 1 over 8 squared, 1/8 squared, plus 1/8 cubed, plus, and so on. Okay, so this is actually called an infinite geometric series. All right, so when you add up 1 plus 1/8 plus so on, I'll write down the formula because I know the answers on the next screen. That's what my teammates have told me, and then I'll prove the formula for you, okay? Because it's always nice to be able to see a little explanation for why these things are true. But the formula for that piece is 1 divided by 1 minus what's called the common ratio. Okay, and the common ratio is 1/8. I'll show you why in a moment in the next screen. But if I have this, let's simplify this and let's try to figure out what this is. So the bottom is going to be 7/8. When you flip it, it'll be 8/7. So I'll move over a little bit more because then I won't run into my head. Flip it over, it gets 1 over 8/7. Do we have an answer choice that is this? I think we do. That gives me 4/7, which is A. Let's see if that's right. That is right. And now what I need to promise you is how did I get that? How did I get that? 1 plus 1/8 plus 1/8 whole thing squared plus 1/8 whole thing cubed and so on. How did I know what that was? Well, here, I'll show you a way that's not completely rigorous because there's a notion of something called convergence. I'm not going to worry about that for today because this is a middle school contest. But if I have this piece, see, one way to think of this is that all of this stuff here, this infinite part is also the same as 1/8 times 1 plus 1/8 plus 1 over 8 whole thing squared plus and so on. Well, you know, the part inside the curly brace, that part inside the curly brace is another copy of x. So if you solve the equation, what I have is I have a 1 from the purple thing plus 1/8, and I've got this x here. This is equal to x. Okay, do you see how this happened? I basically said this part here is 1/8 times whatever it was before. And so if I want to solve this equation, subtract 1/8 x from both sides, and you get 1 equals 7/8 x, which was the formula the thing I gave you, which was 8 over 7. That was the 8/7, and that's what appeared over here. But if you want to see the whole explanation of these infinite geometric series, that's a proper math class. We teach those kinds of things, but of course you can learn that any way you want. With that, let's continue on. Anshul, you get the next one.
All right, guys. We're on to problem number 21, the Königsberg School. It's actually a pretty nice reference. I'm pretty sure that's where Euler developed, graph theory. So a really interesting thing, definitely something cool to learn. But all right, so we're given these 7 pods, right? A through G. Might be a little small for y'all, but and they basically connect each one of these pods a grade, and they connect to, and no neighboring grade can be different by 2, and every the paired one are either by 2 or more grade levels apart, right? So 1 and 2 cannot be connected, 2 and 3 can't be connected, and so on. So I'm just gonna move on to the next page, and there's gonna be a nicer diagram. Always love a nicer diagram. So if we think about this, if we look at this point F, right, it's connected to 5 other points. If you look at this point C, it's also connected to 1, 2, 3, 4, 5 other points, right? And now if we think, right, 1, 2, 3, 4, 5, 6, 7. Let's say we assigned, I don't know, number 4 to F, right? Call it 4, right? Then we have 1, 2, 3, 4, right? Because we can't have neighboring grades be next to each other, right? So we have 4 leftover options, but 5 places to fill. And that's just not possible, right? So what we must do is we've got to put F as one of these ends, either a 1 or a 7, right? So it really doesn't matter, right? Because if we look back into our original problem, right? It says the sum of C, E, and F. So it really doesn't matter. We can just because by symmetry, if F is 1, then C has to be 7, or C is 7. So we'll just call this one 7 for now, and C is 1, right? And now, let's move on. Now we can look at, let's look at G, right? G is the only term that's not next to C, but also next to F, right? And in order for that to happen, this one has to be 2. And if it wasn't, right, let's say it was something else, right, 3, that means one of these has to overlap, right? And that's just simply not going to be possible for 2. So 2 has to be somewhere here, and it can't be, right? Because we can't have neighboring school years next to each other. So the 2 must go here, and then, I wrote too many 2's. 2, and then D is pretty much a sort of opposite example of that, right? This one has to be 6 because it's the only place that's connected to C that's not connected to F, right? So now we're left with, all right, let me cross out the ones we already used. We used 1, 2, 3, we used 1, 2, and 6 and 7. So we're left with 3, 4, and 5, right? And then if you look here, A and B are connected. So A and B can't be next to each other. And we're left with 3 and 5. So if we have left with 3 and 5, 3 and 4 and 5, if we kept it 4 in one of these, then we're stuck, right? We can't put the 3 or the 5 anywhere. So we have to put this 3 and the 5 here, right? It doesn't really matter, 3, 5. Oh, I lied. It does matter because the 2 is connected here. This one has to be a 5. This one has to be a 3. It really does matter. But finally, all we're doing left is a 4 here, right? And now the question is asking us, what would be C, E, and F? It would be 1 plus 7 plus 4, which is 12. Hopefully I did that last part correct. Let's check our work. And, lo and behold, the answer is 12. So really interesting problem. Graph theory is something you definitely learn later in math. It's definitely a really cool subject. So, yeah, pretty nice problem.
Yeah, that was really cool, and I know a lot of you guys probably haven't heard about graph theory before, but if you are ever curious, you should definitely check it out. Okay, on to question number 22. More words. Okay, a classroom has a row of 35 coat hooks. Paulina likes coats to be equally spaced so that there is the same number of empty hooks before the first coat, after the last coat, and between every coat and the next one. Suppose there is at least one coat and at least one empty hook. How many different numbers of coats can satisfy Paulina's pattern? Okay, let's see. Let's try and visualize this, right? So if we have our 35 coat hooks, right, and we have some coats hung on the hooks, each of those gaps before the one before the first coat, the one after the last coat, and every gap between all the other coats have to be the same. And what we're trying to figure out is how many different numbers of coats would work to satisfy these conditions. Well, let's say we had like, I don't know, let's say we had like 3 coats, and I'm just going to put circles as my coats. Well, there's coats before this, there's coats before the first coat, or there's hooks between the first coat, and there's hooks after the last coat. So this is like 4 gaps. And you'll notice that for any number of coats, there's one more number of gaps. So let's say we have C number of coats. So we'll let C equal the number of coats. Well, from what we just realized, that means there's exactly one more number of gaps. So let's say, okay, how about, the number of gaps we can say is equal to C plus 1. Okay, and then each of those gaps has to be the same size, right? Because Paulina likes them to be equally spaced. So if they're the same size, that means each gap is the same amount of empty hooks. So let's make another variable, actually. We can say E is an empty hook. And that means that for each gap, there's E empty hooks, right? So if we have 35 total hooks, then C of those hooks, so if we had 5 coats, we would have 5 hooks are occupied by the coats. And then the rest of the hooks, well, they're empty. They're parts of the gaps, right? So we have C plus 1 gaps, and each of those gaps have a certain number of hooks, E. So we could say C plus 1, which is the number of gaps, times E, which is the number of empty hooks in each gap. So C plus C plus 1 times E. That would equal the total number of hooks, which the question tells us is 35. Now the thing is, we have two variables, but only one equation. So we can't exactly, use a system of equations or anything to solve for our answer, which we're looking for C. But what we can do is we can do some pretty cool factoring tricks. So I'm gonna try moving my writing so that we have a little bit more space. But again, if we use our equation C plus 1 times E, we could expand that out, right? So we could have C plus, distribute the E, we have CE plus E. Okay, we have CE plus C plus E equals 35. And now that I'm looking at this kind of reminds me of something. I don't know if you guys know the trick. Oh, actually, it looks like you guys do. This kind of looks like Simon's favorite factoring trick. And I'm not sure if you guys know what that is, but basically, since we have our two variables, we have CE, and then we have one C and one E, what we can do is we can add 1 to both sides. And you'll see why in a second. So if we add 1 to the left and we add 1 to the right, we can rewrite our equation as CE plus C plus E plus 1 equals 36. And what's nice about this equation is that we can factor it into some really nice terms. So what we can do is we can do C plus 1 and E plus 1. Because you'll realize if we were to multiply this out, we would get exactly this expression right here. So this is a really nice factoring trick called Simon's favorite factoring trick. And if you guys didn't know already, you should check it out. It's really useful. And it showed up on question number 22 of the AMC. So we know that C plus 1 times E plus 1 is going to equal 36. Well, we can't exactly have decimals or anything because these are like numbers of coats we're talking about, right? So that means we can safely just, assign factors of 36 to each of these, right? And well, our only limitations is that there has to be at least one coat. So C is at least 1, and then E is also there's also at least one empty hook per gap. So we don't really have that many restrictions, right? C just can't equal, C plus 1 just has to be greater than 1, so C has to be greater than 0, and then that would also mean that E has to be greater than 0. So if we take a look at 36, and how many factors does 36 have? Let's think. 36, it's a square number, and then all the other factor pairs. I'm pretty sure 36 has 9 factors? Yes, okay. So we have each of those factor pairs, right? And we can use those factor pairs and assign them to our values of C plus 1 and E plus 1 in order to find our final number of...
Oh, I just wanted to jump in. I think, so you're doing, this is great, but I think we said C bigger than 0. I think you actually might want C bigger than or equal to 1.
C equal to 1?
No, C bigger equal to 1. I think you want C bigger equal to 1. Because you said, I think what you did is you looked at C plus 1 and you said C plus 1 bigger equal to 1. But it says, suppose there's at least one coat.
Oh,
So I
yes,
think
okay.
that help. Yeah.
Yes, that's exactly right. So we want C plus 1 to be at least, okay. So that means we want C to be greater than or equal to 1. Wait, yes? Okay.
Yes, that's right. And then the C plus 1 is the thing you care about.
Yeah. And that would make our C plus 1, greater than or equal to 2. Right, okay. So then if we figure out all the factor pairs and assign them, then I'm pretty sure if we're looking for solutions of C and E, then we would have, I think, 7 solutions, because, Is that right? Let's see.
Yeah, you're right. You're right. I think that's right. Because I was doing the same thing. I was working on it at the same time as you, because these are fun. So, maybe let me ask one request. So our tech team has managed to rescue my chat. But maybe if you could put the chat a little bit smaller and on the other side, put the chat over here, then that'll be great. Okay, right. Thank you, thank you. And then maybe shrink it down a little bit. I love having an awesome tech team here. It's nice to see all of you guys. So when I saw what Vivian was doing, I was like, yes, 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 that's exactly right. And so you want to split it. You'll notice I called it C times W. I'll explain that in a moment. But that number of factors is 9, right? Did you do 9 and minus 2? Is that what you did?
Yeah.
Yeah, yeah, yeah. Okay.
Okay.
I want to add one more thought on
Uh-huh.
here also, which is that, see, I wrote this because in some sense I'm watching what Vivian's doing and getting a good idea from it. But when I looked at this problem, I said, what if I just stuck an extra quote at the end? Then it would actually have a repeating pattern. Like you see, you've got empty gaps, and then you've got a quote, and then like a gap, and then a quote, and a gap, and a quote, and then some gap at the end. What if we just stuck a quote there always at the very end, just for fun? If you threw a quote at the end just for fun, you have an extra quote, but then it ends up being that there's this constant pattern of gap, 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 quote, gap, 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 quote. So for me, my W was the gaps plus a quote. It was like the width. W stood for width. But that's Vivian's E plus 1, I think. And then I actually confused myself because I wrote C, but it shouldn't be C. It should be like one more than the quote because you threw something at the end. But it ends up being the same thing that Vivian found. Okay, it ends up being the same thing Vivian found. With that, I'm gonna jump on. I guess I have the next question. Ooh. How many four-digit numbers have all three of the following properties? The tens digit and ones digit are both 9. The number is 1 less than a perfect square. And the number is the product of exactly 2 prime numbers. Ooh. Okay. Well, I'm just going to start playing around a bit because I don't know how to do this. So let's think. So if the tens and ones digits, so I got 4 digits. All right. So 1, 2, and I love the questions when I look at them and I say, I don't know how to start. So the way you start is you just start to write stuff down. Tens digit and ones digit are both 9. I know what that means. Those are 9. Okay. The number is 1 less than a perfect square. That's promising because 99 is 1 less than 100. Oh. So the perfect square is something oh. And the number is the product of exactly 2 prime numbers. Cool. Okay. So, but again, I already made an observation, which is that if it's 1 less than the perfect square, then that perfect square, let's write it down here. So the perfect square, which is 1 more than it, is going to be something, something, 0, 0, which has to be something 0 squared. So it's like some digit. You can't see what this digit is. It looks like a big mess. And a 0 squared. Because that's how I get a 4-digit number. If I had a 2-digit number in front, if I had 2 digits and then a 0 and then squared, that's not good because that's like way too big. Okay. So in that case, there aren't that many options, right? Well, let's see. Oh, this is cool. 1 less than a perfect square also has a nice factoring trick, by the way. Because you know how to factor that. So suppose I have that I'll call it, suppose that was x squared. Well, that square is 1 more than my number. So that means my number is equal to x squared minus 1. You know how to factor that, guys? So that one factors really nicely. That's like one of our favorite, I guess it's not Simon's favorite factoring trick, but it's one of my favorite factoring tricks. X minus 1, x plus 1. And I'm hoping that they're both prime numbers. Okay, I think I have enough information now to try to put this together. So what kind of thing, what 0 squared might work? If I did like 20 squared, that's only going to be 400. That would make 399. That's not a 4-digit number. If I did 30 squared, that's 900 minus 1, which is 899. Not good. So it should start from 40 squared. Okay, let's start from 40 squared. 40 squared, I guess I have to make a list now. So what if it was 40 squared? I'm trying to see if I have space. I'm going to go back one screen. This is just an empty space. Ignore this. This was the old answer. Okay. So if it was 40 squared, that would be 1599, which remember the factorization was going to split into 40 plus 1 and 40 minus 1. That's 39 times 41. Uh-oh. That's not 2 primes because 39 is not prime. So that's how I know that won't work. So that's a no. What if it was 50 squared? 50 squared is 2500, which gives you 2499. And that's going to be 49 times 51. Nope, that's not good either, because actually neither 49 or 51 is a prime number. 60 squared, that's 3600, so that's 3599. That's going to be equal to 59 times 61. Ooh, are those primes? They look prime to me. I think they're actually primes, so that's good. So let's leave that alone. Next one is 70 squared. That would be 7 times 7 is 49, so that's 4899. And that's going to be 69 times 71. That's no good, because 69 is not a square. We'll be done soon. 80 squared. That's going to be 6400, so 6399. That's going to be, and I'm just listing all of these. Maybe you could do this in your head, but I want this live solve to be understandable to as many people as we can. 81 is not a square, not a prime, sorry. So that won't work. Let's keep on going. Do I still have space above the chat? Yes, I do. 90 squared. That's going to be 8100, so 8099. That's going to be 89 times 91. Oh, that's a tricky one. You know, that looks kind of prime, but 91 is this classic number that looks prime and it's not. Actually, I was wrong, by the way. Let's go all the way to 100 squared. That should be an option that we check. 100 squared should be an option because that's going to give you 9999, which is still a 4-digit number. And that's unfortunately not going to work though, because that's 99 times 101 and 99 is not prime. So in the thing I wrote earlier, actually the square, there is a possibility it's 100. Okay, but it looks like I only have one of them. Ooh, okay, I was afraid there might be more. Let's go on.
All right, guys, we're on to problem number 24 here. Really interesting. So we're given a trapezoid, and a really interesting thing you always got to realize first is you got these 60-degree angles, which almost always helps making these right triangles, right? So we're given an AB. We know that AB is equal to DC, and we're given the lines to show it. And you know AB is parallel to BC, so we can form these right triangles. But I think I'll wait before I get a bigger diagram first. So, and our perimeter is 30, right? That's a very important part. So we have this shape now. So, I mean, the first thing I always do is sort of draw these perpendiculars, right, to form these right triangles. And now, let's just call this one A and this one B, all right? Or, you know, you can really call it whatever. So, we know our perimeter is 30, right? And now, how do we solve for this sort of length here, right? This is what we need, I like to solve for, right? Because we need to add up all of our side length to solve for our perimeter. So if this length is A, and this length is B, that means this sort of gap here is going to be half of the difference of A and B, right? And B is our longer side, so we do B minus A, and then we divide by 2, right? So this would be B minus A over 2, and now we have a 30, 60, 90 right triangle. I don't know if y'all know this, but once you have these sort of special right triangles, you always know like the side lengths form this ratio of 1 square root 3 to 2. And this is our smallest side here. That's going to be our sort of 1 side. And if we want to get to our hypotenuse or our 2 side, that would just be multiplying by 2 to solve that length. So this would be B minus A over here. And then we have a symmetric structure, right? We know that DC is the same thing as AB, right? So we have another B minus A here. So now all we have to do is sort of, I'm just going to clear off my screen again. We have A, B, B minus A, and B minus A. So now let's add up all of our side lengths, right? So we're going to get B minus A plus B minus A. So we have 3 of these B's. And then we have A minus A minus A. So we have 3B minus A. And if we look back to our original problem, our perimeter is 30, right? We go to 30. And A can't be 0 or else we just pretty much, you have a triangle, right? That's literally no length. So A must be a little bit. So we can start B off at 11, right? 33 minus 3. Then we can just keep going higher until we have values that just don't work. Or until, we also have to know that B has to be greater than A, or else this gap just doesn't exist anymore, right? So 11 and 3, 12 and 36 minus 6. And let's just keep going. 13 and 9, 14 and 12. And then once we get to 15, we get 15 and 15, right? And this doesn't work, right? We know that A has to be shorter than D, or else we'll get a rectangle, right? That doesn't count. Or actually, it just wouldn't work, right? We wouldn't have, it would just be completely smushed. So that just doesn't work. So we're only left with these 4 possible pairs of A and B values. So only 4 possible trapezoids that satisfy this. So now we can sort of see if I'm correct. And that is the right answer. So really, really interesting problem right here.
Yeah, I want
Okay.
to jump in. I actually like this question a lot. So again, I love playing with these things. So when anyone else is working on them, so am I, as soon as I don't have to do my tech. So back on this thing. See, I thought there was something interesting here where Anshul did something and he subtracted and he noticed this pattern. And what I did is I looked at it first and I said, this piece here, if you slide it over here, then you make an equilateral triangle. So then I know that if I simply slid this piece over here, this would be C and this would be C. And then this is a parallelogram. So whatever that is, that A is this A. So then the game becomes, I need to find positive integers A and C. So A and C have to be positive integers so that the perimeter of this is 30. And then I have all like positive stuff with no minus signs. Because the perimeter of this has 2 of the A's, so that's the 2A, plus 3 C's, 1, 2, and 3. This guy's not part of the perimeter. It's just like a little copy of that, which I used to figure out this. This is like Anshul's special right triangles. I just made an equilateral out of it. So then the game becomes, how many ways can I pick positive integers A and C so that this thing works? Then I thought the 3C is the hard part. Well, when I say hard part, it's the big part. And then I noticed that if 3C is odd, you cannot find the A. If 3C is even, you're good. And with enough gap. So I said, okay, well, the first way I can make 3C even is 3 times 2. The last way I can make 3C even is like 3 times 10. Well, not quite, because 3 times 10 eats up the whole 30. So then I should go from 3 times 2 to 3 times 8 with all the even numbers. And then that would be 4 even numbers. But again, I have the luxury of watching my team do this first. And I try to think of another way. With that, I think Vivian is ready to take us on the last one. And we might all end up piling together. Who knows? Let's see.
All right, yes, time for the final question. And I just started reading it while Professor Loh was explaining his solution. And this looks like a really scary question, you guys. So let's try it out. All right. Well, Michaela's trying to find all the possible ways to draw a path in this 5x5 diamond shape, where each path starts at the bottom and then moves to the top. And then she computes the area of the region between each path and the right side of the grid. Okay, and it gives us 2 examples. And now we're just trying to figure out the sum of the areas determined by all possible paths. Okay, well, first of all, that was really complicated, I feel like, right? And if we're trying to account for all of these possible paths, I don't think the question wants us to actually find them all. That'd be pretty impossible to do with the time limit. So let's try and find a way to maybe get an easier way to figure out the areas or figure out how many paths there are. And one thing that I notice is we have a 5x5 grid, right? And the 2 examples they give us right here, we want the area that's to the right side of the path, which is pretty specific. But what we could do is we could imagine oh, well, what if we were trying to find the area to the left side of the path? That would just be this unshaded area over here, right? And that's actually another path. That would be a third path, right? Because that would just be the same thing. And if we were to rotate, I guess, our grid, that would be as if we had a path right here where I'm drawing in green, and the shaded area to the right side would be like this. And that's the same thing as this purple area, just flipped. And the thing is, if we were to add those 2 areas, I'm going to erase my green, because they make up one full grid, we know that those 2 paths, or the areas formed by those 2 paths, is equal to just the area of the grid, which is 25. So 1 pair of paths equals 25 for an area. Well, we know that every single pair, or every single path, is going to have its exact partner, right? 1 partner that makes it 25. So what if we just figure out how many pairs of paths there are, and then figure out, and then multiply that by 25 to get our total area? But then the question becomes, how do we get those paths? Well, if we're trying to get from the bottom of this diamond shape to the top of this diamond shape, we have to go north, east exactly 5 times, right? We have to move this way 5 times, but also this way 5 times. And the thing is, it doesn't really matter what order, it just has to be 5 of each. So what we can do is we can just figure out how many of the 10 moves it makes to the top of the diamond are northeast and which ones are northwest. And well, we can just say, oh, out of those 10 moves, let's choose 5 of them to be northeast. And then automatically the other 5 are going to be northwest. So we can just do 10, choose 5 in order to get that number. And I don't really know what that number is, so I'm going to do 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2 times 1. And then let's cancel some numbers out. I see 5 and 2, and 2, so I can get rid of my 10. We can simplify, we can cancel out the 3 on the bottom, and we can cancel out the 4 on the bottom. So now we have 3 times 2 times 7 times 6. Okay. How else can we do this? We have 21 times 12. So that's going to be like 21 times 10, right? So 210 plus a 12, wait. Yeah, 21 times 10 plus 2 21s. So that's like 210 plus 42 or equals 252. Now, that's how many paths there are in total. But like we found earlier, 2 paths, or we can pick one path and it will have one exact other path that makes its like complement. And when we add the areas together, it's going to equal our 25. So we can take our 252 and divide that by 2 to get the number of pairs. And then we take that number of pairs, each pair has an area of 25, and we can do that in order to find our total area. So 252 divided by 2 times 25. Okay, 252 divided by 2, we have 126 times 25, and then if we do that, okay, I know 4 25s makes 100, right? So I have, what, 31 25s, that's 3100s, and then I have 2 extra 25s, so I have a 50. That gives us 3,150, so let's hope that's an answer choice. It is, okay, answer choice B.
Wow!
Yay!
Yeah. That's great. Actually, that's usually the hardest question. Yeah, I saw a clap in the chat. That's what you should do. That was a masterpiece. Actually, when I looked at this thing, I was like, oh wow, this looks like a complicated sum. But Vivian's idea of the symmetry of like the stuff to the right and the stuff to the left is symmetric is terrific. So it ends up just being like how many paths there are. And the nice way to think of it is like, what's the average amount of stuff on the right? Well, it's fair, right? So the average amount of stuff is half of the 25. So one very tiny thing that one can do to do this a little bit faster. Again, the hard part was realizing this. The 10 choose 5 she also explained pretty well. But if you expand this out, it's actually useful to write everything and do a whole lot of canceling first, and then do the multiplication. But ultimately, the hardest part was to realize what to do, and that's amazing. Okay, well, it looks like we actually did it in the time we expected, even though we started late. And that's to the credit of our wonderful people, Anshul and Vivian. Actually, for the person who's hosting this tech, could you put all 3 of us on the screen, please? Because then, we can all say goodbye. But I'll also say, as we're pulling them onto the screen, it's really been a pleasure to talk to all of you guys through this. If you like learning in this way, I should say we actually run classes. We run an entire set of classes where you can even learn from Vivian, from Anshul, and from others just like them. And we like to teach in this way where there's this very lively chat. Thank you to everyone for being part of this lively chat. We hope that you had fun with the AMC 8s. I really like doing these live solves because I think that the point of the AMC 8 is not just to get a ranking and a score. It's to actually learn how to do some of these hard problems. And those questions which are at the end are the ones that a lot of times people don't get to. But they're the ones most worth doing. Like, I got a huge kick out of watching that neat symmetry trick that we just pulled out at the end. So with that, congratulations on doing more math tonight, and have a great weekend. See you guys. Bye-bye.
Bye, everyone.
See y'all later.